Hello everybody. Welcome back to In the Loop. This is a podcast by Texas Guadalupe. We are the University of Texas Hyperloop team. I'm your co-host, Gavin Nader. I'm the head of business, and I'm a senior studying economics here at UT.
I'm your other co-host, David Spittler. I'm the head of engineering for Texas Guadalupe and currently pursuing my master's in mechanical engineering at UT. On today's episode, we have Amiee Quon. Amiee was a student here at UT 15 years ago and now works for JPL. Amiee was the chamber test engineer for their Mars helicopter Ingenuity, which has now just recently made 5 successful test flights on Mars. Amiee, thanks for being here. We really appreciate it.
Thanks for having me.
Awesome.
So I guess, yeah.
Take it away.
One thing we always kind of like to start out in asking is just kind of how you got introduced in STEM originally and what kind of drove you to pursue the career path that you went on.
Well, I guess for me, STEM is kind of intertwined with space. I grew up in Houston, Texas, so very close to the Johnson Space Center, as you're probably aware. And space just caught my imagination early. It just seems really neat that, we can send people out into space on spaceships into a very hostile environment and bring them home safely.
So what was sort of your first hard interaction with space or that sort of industry? Did you go to space camp? Did you do any of that stuff?
I did not go to space camp. I was a student in the Texas Aerospace Scholars Program, which is a program for high school juniors in Texas, where you do a set of online activities, learning about space, different kinds of things. And then if you do that successfully, they invite you to I think it was about a week-long experience at the time Johnson Space Center. At the time, it was only a Texas program. I'm not sure if they've expanded the high school program or not. So we got to go to JSC, which was, of course, mind-blowing, and collaborate on a space project. I think at the time you split into 3 different teams, and you have one team that's working on the propulsion side, getting to, I think it was Mars, and then one team that's working on living there, one team that's working on working there, and you come together and put together this whole presentation over the course of the week, as well as learn all kinds of neat things about space. You go on the tours, you get to talk to really cool people. So that was really exciting for me. That was kind of a watershed moment, I guess you could say. Aside from that, also, back in 1997, when JPL landed Sojourner on Mars, that was actually a technology demonstrator, somewhat similar to the way the helicopter is today, and that it didn't really have a science job to do. It was just to prove that you could actually land it and drive stuff around. It made the cover of Time magazine, and I saw it and I thought that was really cool too, that we could drive this rover around, again, Mars, really, really far away. And I kind of made an offhand remark that, oh, gee, it would be kind of neat to work there in the future. I will say I don't know that I necessarily pursued JPL so much at the time, so much as, I wanted to go into the space industry. But when I had the chance to interview with JPL, of course, I jumped at it, and here I am.
So then you naturally, I guess you went to Rice. What did you study there, and sort of were you set on your path to go to space there, and then how did you find your way to UT?
So I did go to Rice University for undergrad. Again, I grew up in Houston. Rice was close by. It was convenient. I studied mechanical engineering there for my bachelor's. I don't know that I was taking any particular space classes while I was there. I did do some internships at JSC at the time during those summers, which was fun. And of course, obviously, if you can earn money, that's a great thing as an undergrad. And then I was looking at places to go to grad school. I applied several places. I ended up picking UT. It was close by, and it was a program that I was interested in. I don't know that I took too many specific space classes while I was doing my master's at UT. But JPL came to recruit at UT through the Career Center, where you do all the, where they set up the interviews and stuff. And that was how I ended up actually getting the interview with JPL.
That's awesome. And then, of course, you had Professor Seepersad while you were at UT, which is how we were luckily able to make that connection with you. I
Mhm.
believe she sent out just like a random email shortly, I believe, after Ingenuity's first flight of like,
Mhm.
hey, here's one of my former students doing really cool things. And,
Well, that's
I just
cool.
had no idea that we had, former UT engineers, working there and doing really cool, groundbreaking things.
Yes, I guess I'd reached out to her. So we were at JPL, of course, we were very, very excited about the helicopter. At the time, we hadn't yet flown. I had been invited to participate in what they called the pre-flight briefing. So they had the program manager there. They had Thomas Zurbuchen, I think he's the associate administrator for space missions, science missions, from headquarters. And I was invited to talk about how we had tested the helicopter, sort of as a background for these are the things we've done so far. This is why we hope to be successful when we actually do the flight. And as such, it was kind of fun. And so I decided to reach out to Dr. Seepersad because I had enjoyed her class and to tell her about that, which is how she found out.
That's crazy because I actually remember watching that briefing
Oh, you
live.
did?
Yeah, and then David sent me the link and was like, "Yo, we have a chance to talk to Amiee." And then I was like, "Whoa, that's crazy!" I was watching it earlier, so that's really cool.
Yeah.
So sort
Shameless
of,
plug for UT, but, what starts here changes the world or maybe other worlds.
Yes.
so for people who don't really know, can you just sort of explain what JPL is and what their role is, like in the greater NASA organization?
Okay, so JPL is considered a NASA center like Johnson, like Kennedy, like Goddard, or Glenn. What makes us slightly different from the majority of the other NASA centers is we are not directly run by NASA, I guess you could say. So we are what's called an FFRDC, which stands for Federally Funded Research and Development Center. We are technically run for NASA by Caltech, the California Institute of Technology. There's another FFRDC in NASA, which is what is it? APL, Applied Physics Lab in Maryland, I believe it is. They're slightly affiliated with Goddard, but really APL is run by Johns Hopkins for NASA. As such, in some ways, I guess we have a little more freedom. We're a little more uh, allowed to take a few more risks, I think. I don't know if that's officially codified, but in a sense, that is effectively what happens for us. Um, and we also have that kind of spirit of academia going on because we're run by Caltech. Um, so what other question? So what have we done? JPL is kind of the robotics center where Johnson could be considered the human spaceflight center where all the astronauts are based and they do most of their training. JPL kind of specializes in robotic types of missions. We do a lot of Earth observing satellites as well, as the ones that tend to make bigger headlines are the ones that we send to Mars or other planets. Like I said, one of the things that kind of really caught my interest early on was when Sojourner landed on Mars back in 1997. That was really the start of our whole wheeled rover program thing. So Spirit and Opportunity and Curiosity and Perseverance are sort of an outgrowth of that. So in that sense, we're excited to see what the future will bring. I mean, as Ingenuity has flown successfully, what kind of helicopters or other air vehicles will we fly in the future and what will they find out? Um, let's see. So yeah, those are some of our very high profile missions. But obviously we've done several others as well. One of the ones that I worked on is called Juno. I was working on an instrument called a microwave radiometer on there. So it had 6 antennas and it was looking at microwaves around Jupiter, trying to figure out what Jupiter, how Jupiter came to be. And every once in a while these days, when you see a new, very close up, usually spectacular picture of Jupiter, that's actually the mission it came from because it's currently sending back data. And every once in a while you see those new pictures.
That's incredible. I guess another question I have. So say, for instance, with something like and the Ingenuity helicopter, is that something that JPL will go to NASA and say that they want to pursue, or will NASA kind of go to JPL and say that that's something that they want y'all to pursue, or kind of like what's the relationship there?
That's a good question. I'm not sure how it works all the time. In this particular case, I think that it was a thing that JPL has suggested, or it came up in during talks that, well, could we do something that flies on another planet? Because obviously, you know that the commercial drone industry has grown and advanced quite a bit in the last 10 years or so. Um, and so apparently we had an older proposal that, hey, maybe we could work on this flying helicopter thing for Mars, that kind of got put away on the shelf for a while until I think it was our center director asked, is that something that we could pursue? And so they pulled out that proposal, and looked through some of the numbers and then proposed it to NASA to see if we could do that. I will say one of the interesting things about being a technology demonstrator, especially with the helicopter, is in a sense we got confirmed for going on the mission somewhat late. Perseverance had already been, it was getting finalized, it was being built. And all along, we spent a lot of time testing this thing. I think our first tests in the chamber were probably back in the 2014 timeframe, not in this current configuration now, but in the early ones that we were trying to prove that we actually could generate enough lift for Mars. And every step of the way, they would give us a milestone. Oh, you have to prove that you have enough lift. Oh, you have to prove that you have enough lift and you can stably control this thing. Oh, you have to do this and that. And we kept having to meet those kind of gates to continue on with the project. Unlike, say, a more confirmed project that's already official, where it's not a, do this thing or your project essentially dies, right now. So that made it a little extra stressful, because we were constantly chasing that, must meet this next milestone or else we're in big trouble. Must meet this further milestone or else we're in big trouble. So that was kind of how we marched along until we were finally confirmed, I think a few years before the mission took off.
I know there was a while there where there was definitely some question about whether powered flight could occur on Mars. How far into like the testing process was it from start to where you finally figured out like, yes, this is definitely feasible to do a full scale test on Mars?
Well, if the question is, did we actually have enough lift? Could we generate enough lift? We found that out fairly early. As background for people who might not be familiar, Mars has a much, much thinner atmosphere than the Earth does. So Martian, quote unquote, sea level, so at the surface, the density is about 1% of the density of Earth's sea level density. So compare that to about 3 times, or 100,000 feet, which is about 3 times the height of Mount Everest. And we don't fly up there. Right. So commercial airliners fly at 30 to 35,000 feet. I think on Earth, the helicopter height altitude record is about 41,000 feet. So you can see that 100 to 41 is quite a bit of difference. So that was our first big question. And the numbers all said that, yes, we should be able to fly. But there's also, when the rubber meets the road, you have to be able to prove it. So first of all, we started out with a small scale prototype. So the blades were only about 12 inches in diameter, whereas the full scale helicopter is about 4 feet. So this was a very small, miniature thing. And what we did was we put it in one of our thermal vacuum chambers. We have a 25-foot space simulator at JPL that we use for just about all the programs we have. But for this purpose, we were pumping it down. So we sucked all the air out, put a little bit of carbon dioxide in because Mars's atmosphere is mostly made of carbon dioxide as opposed to nitrogen as on Earth. And then we were trying to hop this helicopter around. I'm not sure if you have the footage of that particular test from 2014 or not. This was later after we had gotten a more mature model. But back in 2014, we put this small helicopter in the chamber and we were trying to Operate it sort of like you would an RC car, a radio control car, where you have somebody with their hands on the joysticks and, they're saying move. It was only sort of successful. I say sort of successful in that it showed that we could get lift. So that was fantastic. That was great. It meant that we were not barking up the wrong tree, and that this would actually work. You could actually fly it. On the other hand, one of the other things we learned is that even with a super experienced pilot, you can't really, it's really hard for a human to react quickly enough to successfully fly it in the Martian atmosphere, because it turns out that with the thicker atmosphere on Earth, it provides a sort of stability to the airframe, and means that when you give it a little bit of an input, it doesn't react quite as quickly or as violently as it would on Mars. If you do find that footage for the first thing we did, you'll discover that we were able to jump around a little bit, but then the helicopter crashed. So what that told us was, A, we have the lift, which is what we need at the bare minimum. And then B, we were not going to be able to directly control it. So we were going to have a computer-controlled autonomous thing where it does its own flying. Now, there's also other reasons for that, which is that Mars is far away enough from Earth that it takes so long for the radio signals to go from Earth to Mars that you couldn't really get that feedback to control it, with your thumbs anyway. So that was just, one more, well, we definitely have to do it this way. So after that, we started with the larger, full-scale 4-foot models, and then we were tuning our controllers, which is a lot of what we spent all that time in the chamber doing.
So I think
with this joystick test that you were talking about, so essentially, even if we were, in a couple of years, let's say we have our first astronauts on Mars, even then, you believe that it'd have to still be computer controlled as opposed to an actual astronaut trying to steer it?
Yes. Yes.
Yeah. Is this that footage?
Yes, I think this is the one.
Yeah, it's very finicky, it looks like.
So we could make it hop, but I think he was trying to actually make it hover.
It looks a little harder than your normal drone.
It is. The engineer who was flying it is very, very experienced as a pilot, and he was having a hard time.
So can you explain sort of what your role is there, and kind of what that chamber is?
My role and what the chamber is. So the chamber is a thermal vacuum chamber. It's cylindrical. This particular one is sort of a cylinder on end. We have some that are more cylinders on their sides. Usually the purpose of a thermal vacuum chamber is to test a spacecraft as it would be in a space sort of environment without that atmosphere around it. One of the things we know when we send spacecraft into space, you have a side that's facing the sun and a side that's facing deep space. And the temperature gradient between those two sides could be very, very large, where the side facing the sun is pretty hot, and the side facing deep space is super cold. And so one of the things we do is we put spacecraft in those chambers to make sure that they can actually handle that temperature gradient. One of the ways we deal with it, of course, is that we have several ways of dealing with it, actually. There are some that are more passive, which is to say we can paint them. So sometimes you see spacecraft that are white or black in different parts. White, obviously, you're trying to reflect heat away. Black, you're trying to absorb it. We can also put on blankets, which are actually soft goods. We call them MLI for multi-layer insulation. So there's several layers of maybe like Mylar and different things of that sort of nature that are thin. So you make a sandwich of those, and then you actually oftentimes sew them around whatever your spacecraft is. So just like, if you go outside wearing a jacket, it's trying to insulate you. It does the same sort of thing. I mean, that's why some of the things back in Apollo, they painted them gold, because that was also for reflectivity reasons. It's a thermal thing. So that is one of the things we have to do for all of our spacecraft. And so all these different programs have gone through that chamber over the years. It is 25 feet in diameter. I think it's about 85 feet tall. We also have smaller thermal vacuum chambers that we use for testing smaller piece parts or maybe instruments before they go into the full system thermal vac, which is what we do in the space simulator. So normally it's a pretty straightforward test when a thermal team says we're going to bring our spacecraft into the chamber. They have a specified test plan. They might spend a couple weeks in there saying, we're going to do this particular profile. We want to heat it up to whatever. We want to dwell there for however long. Maybe we want to go up and down a couple times, to make sure that works. That's what they're going to do up there. Oh, I forgot to say. Okay, so the other more active way that we can deal with thermal stuff with a spacecraft is you can either put a radiator on it, like actually what you would have in your car, say, where you're running fluid through it to take that heat away. You can also put on heaters as well that you run to make sure that things don't freeze. If you were following the thing with Ingenuity, one of the things that we were worried about early on was we had to make sure we survived the night because it gets really cold at night on Mars, and you have to make sure your electronics don't freeze, because if your electronics freeze, then it doesn't generally wake up the next morning, or at least you're at risk of that not happening. So we were running small heaters overnight to make sure that things stayed, if not toasty, not frozen, right? And of course, you also have to make sure that you have enough battery power, because your heaters, the heaters are basically a resistor. And you're running power. It's kind of like an old-fashioned light bulb, right? It gives off light. These heaters don't give off light, but just the heat that's coming from that resistor. So you have to put in all that power to make sure that you survive the night. So when we were looking at the power profiles, we had to make sure we had enough power to survive the night. And then the next day, after you've used however much power you needed for the night, how long do you need to recharge before you can actually, say, fly, right? So that's one of the things that you have to keep in mind for spacecraft. Thermal is a really big deal. So yeah, back to the thermal vacuum chamber. So we run all the different spacecraft through there to make sure that everything works properly. This particular thermal vacuum chamber is also kind of special because we have a sun simulator in there. So giant lights. I don't remember how many off the top of my head, but we can shine them on a spacecraft to also to simulate sunlight, right? Because again, the sun creates a lot of heat on a spacecraft. So normally you run your test through there, you have your set profile, the people who run the chamber just go through that. Obviously you are instrumented with all kinds of thermocouples and stuff like that, so you can monitor throughout. But if everything is nominal, it's pretty straightforward, right? Sometimes you might break the chamber open in the meantime because you want to test if some of your actuators work. Like if you have things that you have to release, you might want to do one release and then you have to check on them, or maybe you have to reset them before you do the rest of the test. But it's a fairly prescribed process. Now, the chamber operators had a lot of fun with us because unlike some of those other projects where they had that set profile that they were following, we had a test program, and this was our test chamber at the time. So we would tell them, oh yes, we'd like to pump down to whatever pressure that we had decided we were going to use, and then we're going to sit there for a couple hours so we can do one test. But then we're going to need to inspect it afterwards. So come on, pump it back up, and then we're going to open the chamber and take a look at it and stuff like that. So they did a lot of cycling for us, and it's not necessarily what they're used to, but I think they also found it a little interesting as well, because they were following along. How did we do? Did we fly? Oh wait, we got down to pressure, and whoops, one of the sensors is reading wonky. We don't feel secure enough to actually fly it now. We have to bring it back up to pressure without even having flown. Because also along the way, we never really had a backup or a spare. So we had to push the envelope a little in terms of making sure that it's actually doing what we want it to do, that we can fly it and that we can control it and stuff. But you can't push it too far, because if you break it, now you're in trouble too. So there was always that line we were walking throughout. That made things interesting, of course.
So I'm curious, sort of, like when you have to incorporate Ingenuity into Perseverance, like how does that work? And also sort of what is their relationship now that they're both separately on Mars? I think they're interacting, obviously. Sort of what is their relationship like now?
So when you have a spacecraft on Mars, like the Curiosity rover, say, by itself, what happens is that it sends its signals to one of the spacecraft that's orbiting Mars. I think it's Surveyor, and off the top of my head, I don't remember the other two at the moment, but there are a few spacecraft around Mars that it's sending its signal to, and then that gets sent back to giant antennas on Earth, part of the Deep Space Network that JPL also runs. There are several sites. There is one at Goldstone, which is a couple 100 miles maybe east of JPL in the desert. There is one at Canberra in Australia. There is one in Madrid. And those antennas are looking at the sky and trying to get the signals back from those spacecraft that are around Mars, or all the other spacecraft out in the solar system. But different spacecraft are given different windows that they're talking to the Deep Space Network. So from there, then the signals go from the antennas to JPL. Now, with the helicopter is pretty small. It's 4 feet in diameter, but it's less than about 4 pounds. So we don't have space to have a really, really strong transmitter on it. So what it does is it talks to a transmitter box called the base station that is attached to the rover. And then the rover forwards whatever communications up to those same satellites around Mars, which then come back to the Deep Space Network. So without the rover within, I forget what the distance is, maybe a few 100 meters of the helicopter is essentially, communications are cut off with it. It can't talk to Earth anymore, which is why it has to be in reasonable proximity to the rover. Granted, we are a technology demonstrator, so we also most definitely cannot impede or damage the rover, which is part of why the rover backed off to watch all the flights. So that's what the rover is doing for the helicopter right now. It's serving as a relay kind of for that data. It's also taking pictures and or video, well, a whole bunch of still pictures that get put into a video of what the helicopter is doing. And right now, since we've we've moved from being a strict technology demo into more of an operations demo, now the hope is that the helicopter can actually try out the scouting sort of thing, where it looks at things that the rover may not be able to look at. As far as integrating the helicopter with the rover, there is a thing called the deployment system that was attached to the bottom of the rover. So Ingenuity hopped a ride to Mars, tucked up on the bottom under the belly of the rover, sideways, because that was the only way it would really fit, and with the legs folded up. So once it got to Mars, what happened was the deployment system it detached to be able to swing down. And then the legs deployed 2 at a time, the first 2 and then the other 2. And then the deployment system dropped the helicopter onto the ground. So while the helicopter was under the rover, it was being powered by the rover directly, because you're shaded by the rover and therefore the solar panel can't generate any power. But once the helicopter was on the ground, the rover had to back away within, I think they said 24 hours, to make sure that there was enough power on that the solar panels could start generating power before the batteries drained too far. So that was the reason why once the helicopter detached from the rover had to move relatively quickly.
So you said you're now moving, I mean, with 5 successful flights, you've sort of proven the technology aspect and you're now moving into operations. So is it actually part of the mission profile for if Ingenuity scouts find somewhere, will it actually affect the path or the route that Perseverance could take?
I'm not sure how the interaction goes on that. I think that's still sort of TBD. And because there wasn't really much planning of things beyond the first 5 flights originally. I should say one thing at this point. When we talk about autonomous flight on the part of the helicopter, We are still, or at least up until now, we have been giving the helicopter a prescribed flight plan to follow. For the first one that we wanted to take off, hover, turn, and then come back down. Or for the second one that we want to come up, fly out, turn, and then come back and come down. So it's not coming up with those on its own. But once we give it that prescribed map that we want it to follow, then we say go, and then it has to do all that stuff by itself. So it isn't path planning by itself, but it has to figure out how to fly that prescribed path on its own. From here on out, I think there is still some level of planning that like with the fifth flight where we picked up and landed on a new location, I think the science team had some input into which direction we were going to fly in. And so there's that back and forth there, but I don't know exactly how much what Ingenuity finds will inform the rover. I mean, granted, Ingenuity was originally conceived of as potentially having scout capabilities, right? The rover drives relatively slowly compared to what people might think, in part because you think about it, it's like off-roading, right? There's no flat roads. You have to be driving over boulders all the time. So you have to be very careful about where you're going. And especially when you come up to, say, the edges of craters, you don't necessarily know if that's a nice way down, with a nice shallow slope or ramp into there until you get relatively close to it. Maybe you discover that, oh, this is a sheer cliff, so obviously we're not going to go down this way, but then you have to back off and drive around and try again. And that can take a while, depending on where you are. We do have stuff like HiRISE in orbit that can take pictures from orbit, but there's that middle ground that we didn't really have, which is where Ingenuity is sort of that bird's eye view. I mean, there's a reason for that phrase, right? Where it helps you see better, where you get a little higher and then you can look around. So that might actually be helpful with path planning for the rover, but it remains to be seen.
So I know that dust is a huge issue on Mars, especially with solar panels and kind of hurting their efficiency over time. Does Ingenuity have an advantage with its actual blades in terms of kind of removing some of that dust off of the solar panel? And also just, I guess, in terms of battery usage, I know Ingenuity uses like 2/3 of its battery for heating purposes or something kind of insane like that. So how important is battery efficiency and solar efficiency?
Well, obviously, okay. So the solar panel issue came up with some of the prior rovers, Spirit and Opportunity, to be precise, where they were solar powered, and eventually there was enough dust that collected that it was starting to choke off the available power. With Ingenuity, we have discovered that when we fly, we tend to shake off a whole bunch of dust, which makes sense, right? You're flying around, so now you have air moving over you, and you're also probably vibrating at least a little bit because the blades are spinning so fast, that the dust falls off, which is great because then, every time we actually go somewhere, we wipe off blow off the dust, and then we can charge the batteries again. What I think they found after the first flight, the efficiency was slightly higher because there had been some dust that had gotten deposited on the solar array. And after that, it was charging a little bit better. So there's that. Your other question was about battery efficiency. So yes, the stated design intent was that we wouldn't do more than about a 90-second flight. It turns out we've been doing a little better than that. I think some of the flights were up to maybe about 120 seconds because it turned out that we were better with the power than we had thought. I guess the 90 seconds was a little on the conservative side. And yes, it uses quite a bit of power overnight to keep itself warm, which, as we discussed earlier, is kind of vital. You don't want your stuff to freeze or else it's not going to work. But that's also one of the reasons why, at least so far, they've picked to fly the helicopter at what is essentially high noon on Mars. What that does is that gives you all morning to recharge your battery. to get ready to fly. Even in the original, the way the mission was written out, we were never going to fly back to back or even back to back days. The idea would be that you would fly one day, spend the next 2 to 3 days sending your data back and also recharging your battery and getting ready to go again, and then flying again. So it wasn't like something that we would just take off, come back down, think about it for a bit, and then go fly again.
I know in some of the videos I was watching, the team was super excited to get data back to sort of see how accurate their prediction models were. And you sort of talked about like the efficiency was better. How accurate were the actual like flight predictions and the behavior in the air? Now that you have data back.
Oh, I don't have those numbers off the top of my head. I believe we were really pretty close. Everything I heard was that people were very pleased with the way the predictions had worked out. I think, oh gee, we were within a handful of centimeters of, when we were landing back in the same spot for the first couple of flights. The idea, of course, was that we land back exactly where we took off from. I would say within a few centimeters is pretty good.
Yeah.
I think we were within about a meter when we did that longer flight far away and then came back. So I'd say the accuracy is pretty good and that we're doing pretty well.
Yeah, that's just insane to me that like we're so good at predicting that we launched this thing to Mars and it behaves almost exactly how we predicted. It's just crazy to me.
Yes. Well, we were hoping that would be the case, but you never know 100% for sure until you actually throw yourself against that environment and find out what happens.
Right. So kind of to David's point about the environment of Mars, like a lot of the movies depict these big windstorms, right? Is wind actually an issue for Ingenuity, and sort of how do you deal with that?
Interesting question that you asked. So to speak to the windstorms, I think you probably saw that there actually was a dust devil in the last video of the helicopter flying. So yes, there are winds on Mars, and they do entrain dust when they do that, when they blow around. On the other hand, back to that 1% atmospheric density question, they don't necessarily have all that much oomph behind them when it comes down to it. So all that Martian stuff where we're blowing Watney around, not really that realistic. At the same time, the helicopter is autonomous and flying by itself, and it does have to keep itself stable in that wind. So we decided we needed to test it with wind. So we were looking around at all the different wind tunnels available that we could potentially put it in. And it was very interesting. So we were looking at up to maybe about, I think about 20-mile-an-hour wind. That translates to 10, 11 meters per second, something like that. We got that 10 or 11 meters per second number based on what we were expecting from Mars. So that was why that was our goal. And so we were looking at all these different wind tunnels, and we discovered that most of them are high-speed wind tunnels. And we talked to one of them, I think it was the one at Langley, and they said, oh, we think we can get that really low speed that you're looking for, but to do it, we're going to have to idle our fans. And we might have to do some neat stuff with them because the idle, that's actually a lower speed than our normal idle. So we'll have to kind of slow it down a bit. And of course, the automatic controller wants to bring that idle speed back up to whatever it's nominally supposed to be, which is faster than what we actually want for our helicopter. So that was very interesting. Excuse me. The other problem with that was when you pick up and move an entire team and all the equipment across the country, that ends up being kind of a pain. Also expensive, but really kind of a pain. So we were looking at, well, is it possible for us to do wind on our own? And back to that collaboration that we have with Caltech, because again, Caltech is the one that is running us for NASA. There is a group at Caltech that they work on drones as well. And so they're worried about Earth-based wind. So what they did was they put together this giant array of computer fans to blow all this wind at their groups of drones. It's kind of neat because, when you have individual fans, in an array, you can address them separately. So you can have winds that change across the square. It's not all one monolithic blow at X miles per hour. You can have it faster here and then slower across the grid. So we built a smaller version and put it in the chamber. It ended up being a total of 800 and something like that. Almost 1,000 computer fans that we put in the chamber, blowing at this helicopter to make sure that our controller was stable. So we built that and put it together. One of the things you should also know, when we were originally testing the helicopter, like I said, we only had one. We didn't have the luxury of just tossing it in there and, oh, if we broke it, we broke it kind of thing. So we started with baby steps. We actually started with having the helicopter attached to a force torque sensor when we originally flew it, because then what that would tell us is, oh, if we change this flight setting that we think is going to create this amount of lift, does the force torque sensor say, yeah, we're pulling on it in this direction, in this amount, the way we thought we would? And that also means that you're not going to inadvertently drop the helicopter, because obviously with helicopters and stuff, if you stop spinning the blades, you no longer have lift. I mean, maybe you'll get lucky and auto rotate and kind of come down slowly, but you might also just drop. So we had that attached to a force torque sensor to start with, so that we could make sure that we weren't, so that we could test out our controller a little at a time to make sure it was actually working properly. I think that was your question, right?
Yeah, for sure. One thing I like to ask, it's more of a general question, I like to ask sort of our quote unquote space people. Like for you personally, why do you think it's important for us to explore space?
Why do I think it's important for us to explore space?
It's kind of an intense question, but
that's interesting. So I think in part space is, people have a lot of dreams perhaps about space, or aspirations maybe. And I think one of the things that's really neat about space is that it's in the same way that I was inspired by seeing the Sojourner stuff. Hopefully we've inspired the next generation by looking at this helicopter. I know we have captured a lot of the popular imagination. There's a lot of people on Twitter who don't seem to have much other connection to space, who are very, very excited about it. And I mean, obviously we're great. We think that's great. We're really excited about it too. But it's that, being able to show cool stuff to people and having them get excited about that, and maybe think, oh, space is kind of cool, or science is kind of cool, or, what can I do with this? So that inspirational sort of thing, I think is one of the great reasons why we should explore space. Other than that, it can also tell us more about, how did Earth form? What might be in our future? Or, oh, this is a neat geological formation on this other planet. Do we have something similar to that? How was that created on Earth? That kind of thing. Plus, when we go through all these, when we tackle all the challenges, extra challenges of dealing with the space environment, sometimes we come up with neat things that could be of use on Earth, right? Back to that whole thing about the Earth helicopter altitude record is only 41,000 feet. Well, maybe we'll apply some of the lessons from that to here, and maybe we could fly things higher on Earth.
Yeah, that's a good point. And also, like, a lot of the investments we make in space often aren't realized until like a long way down the road. So it's sort of hard for people to understand like why we're immediately doing these things. But yeah, it's a really good point.
There's some of that. Yes, there are definitely spin-offs in terms of technology that we later have on Earth. There's also direct things, right? I mean, GPS would not exist without satellites, right? That's how it works. Sometimes it seems super magical, that it's this thing in the sky that's just telling you, oh, you are here, but it's all because there are satellites sending signals down and triangulating things. So there are definitely ways that space technology helps people on Earth. Plus, the whole thing about space-based internet it takes a lot of work to string physical cable all over the place. So in that sense, having satellites that can beam it down helps.
Right.
I would say I know a lot of friends of mine as well who not very plugged into the space world, but they were keeping up with the Ingenuity helicopter And just it was definitely a huge worldwide event in a lot of ways. And then I also have another question in regards to the helicopter. I know you just recently had your fifth flight. All of these have been, by the looks of it, very successful tests. Is there any kind of life limit in terms of the Ingenuity helicopter? Do you know there's going to be a point where it can no longer fly, or is it just kind of test until you can't test anymore?
I think NASA has given us a cutoff time-wise, beyond which they don't want us to fly anymore, in part because, like I said, they have to coordinate what Ingenuity and Perseverance are doing. We can't get too close because we don't want to damage Perseverance at all. Because again, Perseverance really is the main event here. We were kind of late tag along. So I want to say they said end of August for this operational demo. As far as, is there a hard limit on what Ingenuity can do? I think that's more of a, I mean, we were designed for a 30-day lifespan, right? Because originally that was what the tech demo was. We have 30 days to do whatever, showing that we can fly and stuff. So things weren't really designed with extraordinarily long life in mind. Does that mean that they will hit 30, 60, 90 days and just keel over and not work anymore? Probably not. But, over time, things degrade. The solar panels might start getting scratched. So even though you get all the sand off or whatever, the soil off, they might not be as efficient as they were before. But again, we didn't really take that into consideration, because if you're not intending it to last for, say, 2 years, then you don't really have to care about that, right? So there are probably things that are sort of built in that weren't really taken into consideration that will start eating into the lifespan. I mean, if they gave us unlimited time to fly it, of course. And over time, obviously, the batteries aren't going to work quite as well as they did after you start cycling them that many times. They lose some efficiency. So yeah, at a certain point, we probably wouldn't have enough battery life to fly. Is that probably going to be in 90 days? I'm guessing not, but I don't know for sure. But really, that operational limit that NASA is putting on us is more of a, this is how long you're going to go for kind of thing. And obviously, if we goof somewhere and, it flips over, well, game over kind of thing.
I have another sort of general question. You working in one of the leading robotics labs, I think you might be able to speak to this, but I was asked the other day, if our robots are getting so good at exploring, and obviously we're able to fly on another planet now, why do we even need to send humans into space anymore? So maybe you could talk about what robots are really good at, and then maybe what humans are better at, and why we still may need to send humans.
Robots are awesome, but robots do have limitations. I'm sure you have, okay. It's like the difference between doing everything on Zoom and doing things in person where you can touch it, as opposed to saying to that person in there, no, I meant the one on the left. No, 2 to the left of that one. Go up 1. That's what I was talking about. There's an awful lot of things you can do on Zoom. I mean, we've discovered that over the past year, perhaps more than we realized. But there are still, being there in person to do something is oftentimes much more efficient than sending a robot to do it. That's not to say that robots aren't awesome. Robots are awesome. I would say that, right? But robots are awesome, and they let us do all this stuff now when we don't necessarily have the technology or perhaps the political will to actually send people. Because of course it is a really long journey, and it's a lot easier to send robots to start out with. Cheaper, you can send more of them. We all would have been sad if something happened to them, but it wouldn't quite be the disaster if they didn't make it there as it would if people didn't. So there are a lot of reasons that it helps to have robots along, either ahead of time or along with people. But having somebody there who can just turn their head around and, observe different things is huge. As a person, if you're looking around, you're probably seeing a whole lot more than a robot would if it was just standing there and looking for something in particular. So I don't think it's a thing where we should only send robots and not ever send people. But right now there are reasons that it could be cheaper or easier to send robots. And since that's where we're at right now, I think we should pursue that avenue while we've got it.
Awesome, yeah. And another kind of general question, I think there's like a kind of an understanding that, or I guess like the private space sector is starting to emerge like at a pretty rapid pace. And I'm wondering from you on the inside, do you see NASA's role changing at all because of that? Yeah, do you think like what role do you think the private space sector is going to play in the future versus the NASA role?
Private space definitely helps. It helps expand the workforce, for one, right? You have that many more brains working on a problem. Sometimes they are freed from some of the strictures of doing things the official way, perhaps, or maybe they can do things their own way with a little bit less bureaucracy because they have different processes. I mean, obviously, you still want all the same safety requirements and regulations and all that stuff, but there are some things that maybe it does help to have a different perspective looking at it when you're working on stuff. I would say it's probably, I mean, it's still a partnership throughout. It's nice having different options of launch vehicles. It's really nice that SpaceX can now launch humans so that we've got that domestic launch capability back again. At the same time, it also helps, it frees up some of the NASA work perhaps for doing more of the one-off sort of things that we do, right? That might not necessarily pay off for private industry, but that the government is willing to put their funds behind, right? At JPL in general, we're not an assembly line sort of house, right? We do ones, twos kind of things, right? We had the Spirit and Opportunity rover. Curiosity and Perseverance are similar, but not the same. But, we're not cranking out 10 satellites or something, which is not a crack against the places that do, because obviously we need those satellites. We need them for the GPS stuff. We need them for the TV, the internet, what have you. There's definitely a place for that. But in terms of, the one-off thing, I think the number, it was millions of dollars, right, for the helicopter that they quoted. And would that really pay off for a private space industry? I don't know about that, right? I'm not sure what your actual profit would be off of something like that. And so I think there's definitely a place for the government to, for NASA to support stuff like that. And then maybe we commercialize some of that stuff, and then private space gets in on the game as well. I don't know.
And then I know China just landed their first Mars rover. They're starting to build a space station. It sort of feels like there's this new space race. So I'm curious what your thoughts are on that, and why do you think that's like sort of picking up right now?
Well, I don't know if it's exactly a space race. It is awesome anytime another country gets, makes those cool landings, achievements on other planets or things, because it means that there, again, more brains working on the problem. And again, also, different perspectives working on it. Maybe they've come up with a better way of doing something, or things that people can build off of, leapfrog off of. So that's always awesome. As far as the space race, I don't know about that. On the other hand, maybe a little bit of competition is not a bad thing in terms of, keeping us on our toes and pushing us forward. So I think, we are moving ahead even without all that stuff. I mean, we didn't have this helicopter capability, what is it now, 2 months ago, a month ago? So.
Yeah, and to that point, what do you think is sort of the future of maybe powered spacecraft on Mars or other planets? What is this telling us, and like, what is this going to allow us to do in the future?
Powered spacecraft, or you mean flying? Heavier than air on Mars. So they're actually looking already at larger helicopters for Mars. There are some practical limitations, I think, for how much you can carry. Somebody asked me, could we potentially have like a human scale helicopter on Mars? At least at this point, that looks unlikely, just because of the size that you would need the rotors to be and stuff like that. But it does seem reasonable that maybe you could have a, say, 50-poundish helicopter that could have maybe 5 to 10 pounds worth of science equipment on it, better cameras or stuff like that, which seems reasonable, and you can do science that way. And also, I mean, one of the things with helicopters, aside from that whole bird's eye view kind of thing, is that there are certain places that you just can't get a rover to. The great example is those sheer cliff walls. You're never really going to be able to drive a regular rover straight up a wall. I mean, it doesn't matter how much less gravity Mars has, right? So you can kind of look at all those walls with a helicopter, perhaps. And of course, those walls are oftentimes one of the things of great interest to the geologists, because you have all those strata of different rock types on there. So that kind of thing would definitely be useful for a helicopter. Perhaps, you have a helicopter that jumps around and looks for stuff. It's not being planned for that sample return mission, but, maybe in the future, it's useful for something like that, where you can fly a little bit farther and pick up stuff and then come back. So who knows? As far as in other places in the solar system, there's currently a mission, a helicopter, well, more of a drone with, I don't remember, 6 to 8 rotors, planned for, I think it's Titan, in the late 20s timeframe, called Dragonfly. And so this is more of it's almost like a flying rover in this case, where that is actually going to be doing the science. It's not a tech demo the way we are. And so they're going to be looking around Titan, which is pretty cool. I will say flying on Titan is a little easier than Earth, because their atmosphere is actually thicker than on Earth. So they have different problems than we did with, trying to make sure that we actually could fly on Mars.
So is the Titan Dragonfly kind of the next big JPL project? And also, now that the Ingenuity helicopter is flown, what's next for you at JPL as well?
Titan is actually not a JPL mission. I think that might be an APL mission, if I'm not mistaken, or Goddard, somewhere over there. Definitely not a JPL mission. I think the science types from the helicopter mission have been talking to them somewhat, and I think one of their principal investigator might have been on one of our review boards, but that's not a JPL mission. It's a NASA mission, but not a JPL mission. Your question was what's next for me, and what was your other one?
And then what's the next big project for JPL as a whole?
Oh, the next big project for JPL as a whole, or the next big flagship, I think, would be the Mars sample return stuff. That's going to be a massive undertaking, because so what captures the popular imagination in the Curiosity and Perseverance rovers is the rover. But from an engineering standpoint, those were actually missions with several spacecraft. So you have the cruise stage that actually got you to orbit. You have the descent stage that did the sky crane lowering you on a bridle during the 7 minutes of terror, and then you have the rover itself. There's quite a lot of engineering that goes into the descent stage and the cruise stage as well. Space on the floor, even, as well as just manufacturing time that the machines are taken up by doing stuff for that. So for sample return, it's even bigger than that, because you have stuff that's going to land on the surface, and then it also has to take off again, and then in orbit you have to do what they call break the chain to make sure that you have sealed all the Mars stuff inside, and the stuff outside is that you're not going to contaminate the Earth. So that's going to be the next big thing. I guess we call them flagship missions. Curiosity and Perseverance would be flagship level missions, but we've also done, smaller things as well at the same time. For me personally, for right now, I think I'm going to be working on a project called NISAR, which is an Earth orbiting satellite with a radar-based thing. It's going to be mapping the Earth that I'm just transitioning over to. This one's actually interesting because it is a collaboration between NASA and ISRO, which is the Indian space agency. So we're going to be working on that. It's starting to come together. We're going to take it to the thermal vacuum chamber that I mentioned that we tested the helicopter in, and do other testing and stuff on it. So that's what's next for me.
That sounds like a lot of fun. I know you've also been involved in some mentorship through JPL. I believe the NCAS program is
Yes.
one thing that you've been a part of. What do you think, just in general, the importance of mentorship is, and how you're kind of able to pay that forward to new students?
Mentorship is interesting. Like I said, back in high school when I did that Aerospace Scholars thing, that really made an impression on me. This is actually sort of an outgrowth of that. It's through under the same umbrella. This is called the National Community College Aerospace Scholars Program. And so I really enjoy it. There are people who come through it who are very, very into space. There are also people who are more just generally into science, and space sounded kind of cool, so I signed up for this. Some of them end up really pumped about space after, some not so much, but that's okay. It's more about, sharing that, oh, this is a really cool thing, and these are the different ways that you might be able to do it. In a lot of cases in community, especially I think in community college students, sometimes not all of them were necessarily, well, you have a wide variety of people, right? Same as in any university. You have the people who got there straight out of high school. You have the people who had more life experience and who are going back to it. In general, the people who are going back to it are generally very, very passionate about whatever they're doing because they know for certain this is why they're doing it. That's not to say that people out of high school aren't as passionate, but for certain if they're going back to it and taking time out of their non-school lives to do this kind of thing, they're really into it. But at the same time, some of those people weren't necessarily perhaps as strong in school earlier, and so they didn't think that, maybe they thought that this kind of thing would be out of their reach. And one of the things we show them is, no, it's not. You have just as much a chance as everybody else of getting to this point, and these are the ways that you can do it. So I really enjoy that. And even the people who aren't interested in space, there was one student that I was talking with who hadn't really thought about all the ways that engineering applied to different things. For example, just fasteners, screws, threaded fasteners, right? When you think about all the metrology metallurgy and stuff that goes into them, and how you make the threads the right size and all kinds of stuff, there's a lot of tolerances involved. You have to make sure that a 1/4-20 screw is actually going to go into a 1/4-20 nut all the time, right? Hadn't really thought about just how engineering affects life, right? In all kinds of different things. And so that was really neat. That was an interesting conversation. You kind of see the light bulb go on that, hey, this engineering is really cool stuff. You don't have to be working on space if that's not your thing. But there's all kinds of engineering on Earth that's just really neat.
So do you have any tips or any advice for people who want to be like you and want to work on these world-changing projects?
Yes. So you do have to obviously have some science or engineering or math background or computer science or something like that. I would say, well, actually, I guess I would say, even if you're not interested in space, I would recommend seeing if you can find internships or research assistantships or things like that. The reason being, you discover more about what the work is like, or things that you might not necessarily have known about, that are really interesting to you. For example, one of my jobs is to do what's called mechanical ground support equipment, which is like all the tools and stuff that you use to build a spacecraft, which I hadn't really thought about before I actually got to JPL and got this job, right? But you can't just take your spacecraft and sit it on the floor. And all this stuff, that we were talking about with that fan wall, with all the force torque sensors and how we were mounting the helicopter and stuff, that's all ground support equipment. But you don't really think about that because you're like, helicopter. So there's all kinds of jobs. Back to the whole thermal thing, all the thermal blankets and stuff. There's a whole lab that we have that their only job is to sew these thermal blanket things. And they do all the patterns for it. And then they cut out the stuff and they fit it up and they actually sew it, like needle and thread sewing. and stuff like that. And then you have the thermal engineers who are looking at how many heaters do we put on here, how big, what kind of power level. There's so much stuff that goes into it. It's really neat.
I have one more quick final question on the Ingenuity helicopter that I kind of just remembered. If I remember correctly, a small piece of the Wright brothers plane from their initial flight is on the Ingenuity helicopter as well. I guess I'm just wondering, one, how is that kind of coordinated and being able to like have that happen and the initial idea there, I'm sure. And then also, what is it like personally for you being able to be part of something as big and historic as that?
So the Wright Flyer thing, I believe the Smithsonian has the actual Wright Flyer, and so that's where we got it from. I can't tell you exactly where the idea came from. I do know that we were regarding this first flight as sort of a Wright brothers moment in that, this is the first flight on another planet. So I think somebody might have heard that and gotten a bright idea that, hey, can we tie in the Wright brothers somehow? I know it went through very high levels at NASA. Obviously, for something like that, you have to go pretty high up. But I don't know exactly how that came to, how that played out. As for me being part of it, it's kind of amazing. I mean, I was thinking about it. I don't know that I will necessarily be involved in something as big as a first like this again, right? Because projects have a certain lifespan. We plan them years in advance. And I mean, how many firsts are there? Yes, there are a lot of different firsts, but what are the chances that I will be on the next, I don't know, first submarine on an ocean world or something? I don't know. So that's really cool. Now, at the same time, it's pretty powerful to be working on the Curiosity rover as well. When I did that, I mean, that was kind of my first big project. And, everybody's on the edge of your seat when it's landing night, and hoping that everything works out properly. I mean, we've done everything we can, but back to that whole thing, you've never actually seen that environment until you see that environment. So it's always it gets a little emotional when, you get that first confirmation back that, yeah, it's there and everything's okay, right? I mean, because there's always a possibility that you left a smoking crater somewhere, and then everybody's really sad. But yeah, it's pretty cool, knowing that, gee, I worked on the first helicopter on another planet. It's pretty awesome.
Well, based on your track record, I'm not going to be surprised if I see Amiee Quon on the next groundbreaking project. I just want to thank you again for coming on. This has been awesome. I definitely learned a lot. I think it's such a cool project, and it's really cool to have like a firsthand experience. And yeah, this is just one that we've been really excited about. So thank you.
Awesome. Well, thanks for having me.